let's do some line integrals. So I have a vector field here, and you can see it's this, which is kind of small, and I'm going to let c equal to 1 just to make things easier. So this is x hat plus y hat. And we want to do, we can think of it as work, right? Line work is a line integral. And I want to go from point A to B, where A is the point 1, 0, and I want to go to 0, 1. So let's just draw that right here. I should have a ruler. I don't have a ruler. Let's use this. Okay. So let's just draw this out here. Here's 0, 0. And I made that vector field. It's a quiver plot with real Python, just to make some lines there. Okay, so we're going from here to here. We're going to integrate along that line. So I want to do this analytically, and then I want to do this numerically, and then I want to use a different path, just for fun. So it's really about how do we do a numerical integration, but I want to have the analytical version first. So let's do that. So work is the integral from A to B of f dot dr. Now, in the normal world of not using a computer, I can say the vector f is x hat plus y hat, and the dr vector, dr is always in Cartesian coordinates, dx x hat plus dy y hat. No, dy y hat. Okay. Now, this is a sketch right here. Here's our diagram. We're going from here to there, right? We're going this way. So it might be tempting to say, oh, dx is negative because I'm going in the negative x direction. No, that's not true. That's dx, right? I mean, that's dr. dr is dx x hat dy y hat. The direction comes from the limits of integration. So let's just do this. Let's take the dot product. I can do that and set this up as an integral. Work is the integral from A. I'm just going to leave it generic A to B. That's A. That's B. Of f dot dr. So f dot dr is going to be x times dx, easy, plus y dy. And that's what I have to integrate. Well, I can separate that into two integrals, and that's going to be equal to the integral of x dx plus the integral of y dy. And so this only depends on x. Yay, that's kind of nice. So this goes from x equals 0 right there. No, it goes from x equals 1. Starts right there to x equals 0. Let's put x equals. And y goes from 0 to 1. So this is not too difficult to do, right? We can do this integral. Let's do it. So the integral of x dx is going to be x squared over 2 from 1 to 0 plus y squared over 2. And this is a dumb, silly, and trivial integral, that's for sure. But we're really doing this so we can do it numerically. Okay. From 0 to 1. Okay, so this is going to be 0 minus 1/2. And this is going to be plus 1/2 minus 0, so it's 0. So the work done is 0. Yay. Okay, now we're going to do this numerically. So numerically, in this case, what does this integral mean? This integral means that I'm summing up x dx for an infinitely small dx over an infinite number of pieces. But now I want to do a finite number. So we're going to do a finite number. And we're going to do it a little bit differently. So let's draw a picture. So I still have this, f equals x hat plus y hat. I'm getting out of control here. I'm thinking ahead. That's my problem. So here's my x. Here's my starting location. Here's my ending location, A, B. What I want to do is literally just take a dr as a vector. I want to move a step dr. And during that step, I can calculate the work. I'll call it d work is going to be f dot dr. And so this is an actual vector. We could kind of guess what it is. We're going to find out what it is in just a second. And f is the value of f at some point over that interval, which is not constant, but we will assume it is. So we can find f at the point right here and then use dr for the step size. And then we'll do another step, and another step, and another step, and I need to curve a little bit, and another step. And then we'll calculate the work, add them all up, done. Okay. And then you can make the step size as big or as small as you want. So how do we do this in Python? Well, we're going to use a trick. The key is to find, I need to move my point, and I need to find dr. So the point's pretty easy. I can just use a vector location for this. I'm actually going to use a mass. I'll do it two different ways. I'm going to do it visually first because I think that will help. And then I'm going to calculate dr. That's the hardest part. So dr, let's calculate this vector. I'm going to call it RAB. Right there. RAB is the vector from A to B. So that's going to be RB, the location of B, minus the location of A. That's that whole step. That's the whole thing I want to do. Now, my step size I'm going to call S. And I'm just calling it that because I don't want to confuse with other values in there either. So how big is my step size? I don't even know. I'm going to pick some value of S. And I can write dr as S dr hat. What's the direction, the unit vector for dr hat? That's the same thing as S r hat. So I have a step size in the direction that I want to go. So how do I find r hat? Well, if I know RAB, then r hat is just going to be the vector RAB divided by the magnitude of the vector RAB. And that's it. So then I can just keep stepping until I get to here. Now, I do have to, in Python, I'm going to have to think, how do I want to end my loop, right? Because I'm going to start, move, start, move, start, move, start, move. Well, what's the condition that I have when I meet this? What I'm going to do is to say, as long as the x value of my location is greater than the x value of that, I'm going to do it. Because I can't do it as a vector, right? Because how do you say this vector is bigger than that point? That's kind of hard to do. There are ways to do it, but I'm just going to use the x-coordinate. I'm going to actually draw, I'm going to put a point there, I'm going to make a sphere, I'm going to put a point there, and then I'm going to have a ball that moves, just to visually see what's going on. So let's go ahead and do that in Web v Python right here. Okay, so I got Web v Python pulled up. And I'm going to make these things. I'm just going to make the origin. It's a sphere. I don't even actually have to label it. The position is the vector 0, 0, 0. And this is just so I can kind of see the scale of everything, right? The radius is going to be small, let's say 0.01. Now let's make point A. I'm going to call it PTA. It's also a sphere. Position is equal to vector where it starts, 1, 0, 0. And the radius is also 0.01. And then point B is a sphere. Position is vector 0, 1, 0. Radius is 0.01. And let's run this and see what happens. Okay, so there's my points. There's my origin. They're a little small. Let's make them a little bit bigger. Let's make these all 2, 2, 2. That's better. Okay, so there's my origin. I'm going to start from point A. I'm going to move to point B. And this is just so we can visualize what's going on. Yeah. So now I'm going to make the mass. I'm just going to call it, it's what I'm moving, mass. It's the sphere. Its position is at point A.pos. Remember, point A.pos is this vector right here, right? So that's when we talk about 3D objects, it's easier to talk about positions as a property of that object. Let's make its radius equal to 0.04 and color equals color.yellow. So it'll be on top of point A, but there it is right there. Okay. Now I'm just going to move it. I'm not calculating the work, I'm just moving it. Now I want to calculate, let's do this too. Make trail equals true. Now I want to calculate the r hat vector. So I will say RAB is equal to point B.pos minus point A.pos. And then R hat, let's just step it over here. S is going to be equal to 0.1. I'm going to do a big step right now. And then we can make a smaller step later. I want to be able to see it. And then dr is going to be S times norm RAB. So norm is a function built in WebVPython that returns a unit vector. So I don't have to do the R over R hat. That all does it for me. Let's just print dr and see if we're on the right track here. Okay, so this is my R hat vector. It's small because I multiplied by 0.1, but you can see it has this negative x hat, positive y direction, which is what we want. We're moving in a 45-degree angle, so that seems legitimate. Now I'm going to just move the ball. So while mass, I should have called it a ball, mass.pos.x is greater than ptb.x. So, pt.pos.x. Then do the following, right? So ptb.pos.x is my x location of my final thing, and then the other one's my x location of my current thing. So I'm moving until I get, as long as I'm greater than, my x value is greater. We could do y. I did x. Let's do a rate of 10 so that we can actually see it move. So this says don't do more than 10 calculations per second. So I'm just going to move the mass. So I can move the mass by saying mass.pos equals mass.pos plus dr. Dr is my step size, right? That's all I have to do. Let's run it. And there you go. And you notice that it went over a little bit. It went over a little bit because it was less than that, and it moved it forward until it was it's greater than that. Then it moved it forward until it was less than that. And that's fine, okay, because I had a huge step size, so it's not that big of a deal. Let's just make an arrow. Let's just for fun make an arrow and see what it'll look like. I'm not even going to give it a name. Arrow position equals mass.pos. Axis equals dr. And so we can see those little steps. And let's give it a color of cyan, color.cyan. It'll just look cool. Oh, now let me turn off the trail so you can see a little bit better. I'll just put this as false. And so there's all my little step sizes. I'm actually going to make, let's make our step 0.3. There you go. So step, 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 step. So those are my dr vectors. I think that looks kind of cool. Okay. Let's go back over to the code. I'm going to turn that off. I'm going to make this true. I'm going to make my step size smaller, 0, 1, and I'm going to make this go faster. Like that. Yeah, that looks pretty good. Now we can see that it's going to stop very close to the mass. You won't be able to tell the difference. Now I want to calculate the work during each one of those steps. That's 100 steps. Well, that's, yeah, more than 100 steps. So to do that, I'm going to set work equal to 0 because I'm going to calculate the work along each step and add it to the total. But to do that, I need a total. So I'm going to start with the total of 0. Down here, I'm going to calculate the work. dwork equals dot f. Oh, I don't have f. Let's calculate f. So f is equal to vector. It's going to be my x, y, 0. So my x value is the x value of my mass. So the x value is going to be mass.pos.x. The y value is mass.pos.y and 0. So now I have the vector, and it's going to change as the mass moves. I can take the dot product f dr. That's it. I have to give it two vectors. It gives me back a scalar value. Now I can add that to my total work. Work equals work plus dwork, and then we'll be done, and we can print out the work. Print work equals work. And it should be technically in joules. My units are bad, but whatever. Okay, let's run it. Remember, we did this analytically, and we got 0. Here it goes. And then we don't have to do the visualization. And I get -3 times 10 to the -3, not 0. But 0-ish, right? Of course, if I make my time step smaller, my distance step smaller, it'll give me a better value, and that's still a pretty good answer. I'm pretty happy with it. So, okay. And we can do we can change the point B to wherever we want. But I want to do a different path. What if I wanted to do, that's a curve path. What if I want to go along a circle from here to there? Let's go to the paper and see how we would create a circular path. And if this is a conservative field, which it is, then the work done along this curved path should be the same. Okay, so switching to the paper. Okay, I need another sheet of paper. How do we move? Because if I can move along a curved path, I'm done. That's all I need to do is move along a curved path. So this is, here's where I want to end. Here's where I want to start. And I want to move along this. Oh, that's a bad circle. That circular path. So in general, if I start there and I can pick a point on my circle, so I can then calculate the vector dr, right? And so in this case, dr is going to change direction each time. So that's something that we need to take into account. We can't just set dr and be done with it. Let's do a little trick. Let's call this R1, the initial position. Can I calculate the new position, R2? There's a lot of ways to move in a circle, but I like this way. And if that's at some angle theta, then R2 is going to be the magnitude, I'll just call that R, the radius of the circle, times the vector cosine theta x hat plus sine theta y hat plus 0 z hat. So now if I know the new location, then I can find dr. I can just say dr is equal to R2 minus R1. Right? It's just the displacement. And now, how would I find the next point and the next point? What I'm going to do is just calculate these positions and say theta equals theta plus delta theta. So I'm going to have some delta theta, the amount that I move. So I'm moving with an angle. If you want to move in a circle, I'm basically using polar coordinates. And so that makes more sense. Otherwise, you're going to have to find the direction of the change in vector here. So let's just pick a value for theta at 0, pick us a large delta theta, and move along there so we can see it moving. Okay. So going back to Python. Here we are. Okay. Same code. So I know I have not going to change that. RAB is fine. I don't need to change that. I do need this dr. I'm going to change that. Let's just pick theta equals 0, d theta equals 1 over 10. No, pi. Let's say 0.1. I'm just picking a value, 0.1. Okay. And let's make the rate 10, so slower. So the first thing I need to do here is what I'm going to do is I need two R values. I need the old R value and the new R value. So let's call R old as the vector. Our radius is 1. I guess I should put that up here. R equals 1. So R old is going to be R times the vector cosine theta sine theta 0, which we already know that it's 1, 0, 0. That's fine. But that's my old value. Now I'm going to calculate my new value. So I'm going to go ahead and let's put let's go ahead and increase theta. Theta equals theta plus d theta. And now I can calculate my new R value. R new is going to be equal to the same thing. Right there. Now I can calculate dr. Dr is just R new minus R old. Now I have dr. So the rest of this is fine. Right now I calculate the force. It's based on the position. I'm using it at the beginning of the position. And then I'm going to calculate the work and add that to there. And then I'm going to move the mass. So now to do that, I'm just going to say mass dot pos is r times vector cosine theta sine theta 0. I think this should work. Did I increase theta? No, I didn't. Now I need to also increase my value of theta. Theta equals theta plus d theta. And I need to set my old value equal to my new value, right? So I need to say this new, I'm going to recalculate new, but I'm going to need a new old. So I'll say r old equals r new. I think this should work. Let's just see. There you go. Moved along a curved path. And let's see what the work is. Not 0, but close. So I'm pretty happy with that. Let's just do this just for fun. Let's turn off the trail. And then down here, I'm going to make this a little bit bigger, 0.3. And let's show this arrow for DR, just so we can see what it looks like. Pretty cool. And it went over a little bit. That's fine. So there's my DR vectors, and it is a curved path. I'm pretty happy. Let's go back over here one more time. Change d theta to 0.01, the rate of 100. Don't show the arrow, and turn the trail back on. And I will give you the link to this code. You know I'm going to do that, right? And let's run it one more time. Looks nice. And it's super tiny work. So, win. The end. Hope that helps. Oh, I did say I was going to make it without the visualization. I'm not going to do that. But I'll just tell you what you would do, because it's not a big deal. You don't need the visualization. I think to learn and see what's going on is very useful, but you don't need that. You can just turn all these into just vectors, right? I don't need the point A as a sphere. It could just be a vector. The mass could just be a vector. I just call it R. And then I have no visualizations, and it will run a lot faster, and you can just get the calculation. But there you go. That's it. Line integrals, Python, and paper. The end.